You've probably heard the words architecture and organization thrown around when people talk about computers. And hey, they sound pretty similar, right? A lot of people use them interchangeably. But they are absolutely not the same. In fact, understanding the difference between them is one of the most fundamental concepts in all of technology. So let's break it down. A great way to think about it is like building a house. First, you've got the architect's blueprint, the plan. And then you have the actual construction, the build. One is the grand design, the other is how you actually make it happen with bricks and mortar. And that is the core idea we're going to dig into. The huge difference between what a computer is designed to do and how it physically gets it done.
All right, let's start with that blueprint, computer architecture. This is the high-level plan. It's everything a programmer needs to know to write software that will actually run. Think of it as the official rulebook for the system.
Okay, so here's the more textbook definition. But look at the key phrases here: visible to a programmer and logical execution. Architecture doesn't care one bit about the brand of memory chips or how thick the wires are. It is all about the functional behavior of the computer as the software sees it. And this quote just nails it. If you're going to remember just one word for architecture, make it what. What can this machine do? What commands does it understand? What are the capabilities I, as a programmer, can expect to work with? That's architecture. So what does that actually look like in practice? Well, things like the instruction set, that's the list of verbs the processor knows, like add or store, or how many bits it uses for numbers, even the basic ways it handles input-output. These are all fundamental rules of the road that a program has to follow. And now, for the other side of the coin. If architecture is the blueprint, then computer organization is the build. It's the construction crew, the power tools, the specific materials you use. It's all about the physical reality of bringing that blueprint to life. And the definition really says it all: operational units and their interconnections. See, now we're talking about the real physical hardware. How are the processor and the memory actually connected? What signals do they send back and forth to get the job done that the architecture promised? And there it is, the perfect parallel. If architecture is the what, organization is the how. It's the nitty-gritty, behind-the-scenes implementation. How fast is the connection to the memory? What specific kind of memory technology is being used? These are the organizational choices that turn an architectural plan into a working machine. So we're talking about things a programmer really never sees or even needs to think about. The specific control signals firing between components, the physical interfaces, the type of RAM chips. It's all happening under the hood. A program just says, save this file, right? It doesn't care how the hardware physically manages that process. That's organization's job. Okay, I know this can all still feel a little abstract, so let's make it super concrete. We're going to take a really simple problem and see how both of these concepts work together to solve it. Yep, that's it. We're going to break down 2 + 2 = 4 from both the architectural and organizational points of view. It might seem almost too simple, but trust me, it highlights the difference perfectly. So let's put on our architecture glasses. From this point of view, what matters are the rules. The architecture guarantees a few things. First, that an operation for addition, the plus sign, actually exists. Second, that the number 2 is a valid kind of data it knows how to work with. And third, it defines how that data is represented, in this case as binary. It's the rulebook for the math problem. Okay, now let's switch to the organization glasses. We're looking at the physical journey now. First, the system has to physically fetch the 2 numbers from memory. Then it sends them along physical pathways to a specific piece of hardware called the arithmetic logic unit, or ALU. The ALU is like the processor's dedicated calculator. It's the thing that actually does the math. Once it has the answer, it sends the result back to be stored in memory. That's the physical how to the architecture's logical what. So, what's the big deal? Why does any of this matter? Well, it matters because this separation, this split between the blueprint and the build, is one of the most powerful and important ideas in the history of computing. It's basically the reason our entire digital world works the way it does. This table really sums it all up beautifully. Architecture is the logical what that the programmer sees. Organization is the physical how that's totally hidden from them. And that's exactly why you can have 2 processors from, say, Intel that share the exact same architecture, meaning they can run the exact same Windows software, but have completely different internal organizations, giving them totally different speeds and prices. And this right here, this is the magic trick. By keeping the architecture, the what, the same, we can run the same piece of software on a clunky laptop from 10 years ago and on a brand new cutting-edge machine. This separation allows the organization, the how, to get better and better and better. Engineers can make computers faster, smaller, more power efficient, all without breaking the software we depend on. It is literally the engine of progress. And that leaves us with a huge, exciting question, doesn't it? The basic architectural rules of computing have been surprisingly stable for a long time, but the organizational methods, the physical how, are being completely reinvented all the time. We're talking about everything from quantum computers to processors that use light instead of electricity. The blueprint might stay the same for a while, but the ways we can build, well, we're just getting started. It really makes you wonder what the computers of tomorrow are going to look like under the hood.